Hello and welcome back. Today we're going to build a camera, specifically an orthographic camera, to be able to display our 2D scene from a camera's point of view. So we'll be able to get to this point where we have some camera controls down here. We can change the height of the orthographic camera, which essentially zooms in and out and even into the negatives. And then we can also move the camera's position and rotation. So stick around while we build this together. As always, please remember to subscribe and give me a big thumbs up, as it really does help the channel. And now let's talk camera theory. So what exactly is a camera, and how do we use it to render something on our screen? Well, a camera, you can think of it as an eye coming from a point in space that looks out into the world. And let's say we have a sprite here with my bro on it. The job of the camera is to take every point that it sees in the 3D space and convert it into a 2D coordinate that can be seen and maps correctly to our screen. Now, if you remember, our screen coordinate system at the base OpenGL side is from -1 to 1 in both axes, right? This is called normalized device coordinates. It means that regardless of the size of your screen, whether it's vertical, horizontal, a widescreen monitor, a non-widescreen monitor, it will always go from -1 to 1. What our camera can do for us is take these 3D points that are somewhere in 3D space and convert them to some point that maps correctly on the screen. Now, there are two types of cameras. What you're looking at here with this sort of pyramid style view is called a perspective camera, and its job is to make things look 3D on a 2D screen. So for example, if this sprite here was actually rotated in 3D space, where these points are closer to the camera than these points, in perspective projection, what you would see is that the points closer to the camera appear larger. So you'd see something that looks like this. Even though it's on a 2D screen, our brain can look at this and perceive it as a 3D object that happens to have been rotated. This conversion from 3D points in space to 2D points on a screen is called a projection. We're basically taking these 3D points and projecting them onto a different space. And that's why the first matrix that we care about for a camera is called the projection matrix. Its job is to project these 3D points onto a 2D screen. So when we're talking about a perspective camera, we're just saying that it has a perspective projection matrix. And what that allows us to do is define something like a field of view, which is the angle that you see here. With a narrow field of view, you would see less of the 3D objects, and these would appear larger or closer to the camera. Whereas a larger field of view, you'd be able to see more of the world, but the points themselves would look a little bit further away and potentially a little distorted, especially when comparing a 45-degree angle field of view to something like 175 degrees. So you might be wondering why I'm talking about perspective projection when we're building a 2D engine. Well, it's the same concept for 2D, right? You know that in our current 2D engine, we have an X, a Y, and a Z position. And we just happen to be using Z for ordering, right? But it's the same thing. Somewhere in 3D space, a sprite might live in front of another sprite, which means this sprite should cover this one at the back. But we don't necessarily want things to look like they're in 3D space, right? We want a different kind of projection matrix that still allows us to view the scene, but that makes everything look flat like you would expect in a 2D game. That's where orthographic projection matrices come into play. Now, if this is a perspective matrix with the angled field of view there, an orthographic projection matrix is more like a rect. So regardless of where the sprites are and whether or not they're rotated, they will still show up as flat on our 2D image. And if we were to take this projection matrix and take it to a screen, you would see the A and B would look like this. A and B, again, even though these points are closer to the camera, the orthographic projection, it's not angled out, it's flat. So everything's going to get projected just like this. And it will look flat on the surface, so our B will actually look like this still. Now notice, it is a little thinner than A, even though they might have the same width, maybe not here since it's not drawn to scale. But B will look thinner because it is actually rotated, which means it takes up less pixels when you're going across here. And it will still look a little rotated. But the point is that the vertices themselves will be straight. They'll be flush. They won't be curved like this. So that's the projection matrix. And with orthographic projections, just like we had field of view for perspective, for orthographic, we usually have height, which is just the height of the box, which I've drawn from the top-down view so you can't visualize it properly, but it kind of looks like this. Right? This is the camera, and this is your sort of projection cube, if you will, and this is your height. So again, with a lower height, let's say it's only this high, what you're effectively doing is zooming in, and everything seems bigger. So those are projection matrices. Now there's also a second matrix that we usually care about for a camera, and that's its position, because if my camera moves to the left, my projection matrix might end up only covering this much space, which means it looks like A has moved to the right. And that's what you'd expect. If you move a camera to the left, everything that the camera's looking at seems to move to the right. So how do we handle a moving camera? Well, that's what's called our view matrix. And our view matrix is a little simpler than the projection matrix. What it does is it takes the position, rotation, translation of the camera, and it inverts it. So if the camera moved, let's say, -3 pixels on the x-axis, everything else should be rendered +3 pixels on the x-axis to compensate. Another way to think about it is that cameras are just a set of instructions of how we render things from the scene. So the camera itself is just containing these two matrices, and we can think of a scene as being rendered through a camera. Even if we don't have one, the camera just happens to be an orthographic projection from -1 to 1. But if we think of the camera as a series of steps that we take out on every vertex in order to properly render it on the screen, then it starts to make a little more sense. Take our scene. If we want to render the A sprite, we look at each vertex of the A sprite and take its 3D position in the scene. We then take that vertex and multiply it by the camera's projection matrix, which gives us something like this or something like this, depending on the projection matrix that's used. So that gets us from 3D world space to 2D screen space. And now to compensate for camera positions, we look at the camera's view matrix and invert it. We then multiply the point by that view matrix as well, so that we can see the resulting effect on screen. One small correction, that while I was recording this, I mentioned that we multiplied the 3D point of the vertex by the projection matrix first, and then the camera's view matrix. This is actually in reverse order. What you want to do is take the 3D position in world space of the vertex, multiplied by the camera's view matrix, which is in world space as well. If I move 3 meters to the left, I want to move the vertex 3 meters to the right, regardless of the projection. So you actually take the vertex, you multiply it by the view matrix first, then you've got a new point in 3D space that you can multiply by the projection matrix to change the coordinate system that it lives in, from that 3D world space to that 2D screen space. I'll continue to say that we multiply by projection first and then view, but know that this is actually out of order, and when we write this out in the shader, we'll actually be multiplying it in the correct order. So going through the steps, this point here, let's assume my camera is at -3, will be multiplied by the projection matrix and then multiplied by the view matrix, which again is the inverse of the camera transform, and I might get a point here in normalized device coordinates. I'll do the same for all of my vertices, and you can see that I end up rendering this sprite correctly. If the camera keeps moving to the left, I keep moving the sprite to the right because each vertex is being rendered through the camera. And as you can imagine, the way we're going to pull this off in code is that in the vertex shader, where we currently have model matrix times the position, this model matrix is the position of the sprite itself. So if the sprite is at +3, we multiply it by a matrix that gives me +3. This is because if the A sprite moves to the right, it should look like it's moving to the right on screen. Now we can add two additional matrix multiplications here in the vertex shader, the projection matrix and the camera view matrix, which again is the inverse of the camera transform. And this is how we finally end up with vertex positions that are being rendered through our camera. And once we modify the camera's position or projection matrices, these vertices will be rendered differently according to those matrices. So that's the theory. Let's go ahead and actually build this thing. So as always, the first thing we're going to do is create our class. Now the main thing our camera needs is that projection matrix, right? And we need to include GLM here. Perfect. We're going to build an orthographic camera today. We care about the height, so let's track that here. And there's also two additional components. It's the near and the far clipping planes. So when something's too close or past to the near plane, it won't be rendered. And when something's too far away, past the far plane, it also will not be rendered. So let's track those as well. Now we can have our constructor. We'll also have a copy constructor here. Copy constructors are going to be important when we start dealing with things like entities and components because they will be copied around a little bit internally. So we'll make sure we have a copy constructor here. And then let's just write some getters. So inline float. And then some setters as well. Now usually you set all three of these at the same time because that's how you define your orthographic projection. So we'll also have a void set ortho here, which can take all three at the same time. And maybe we'll have some default values here as well. So we'll have near is 0.f and far we can say it's 100.f. Just arbitrary. Perfect. And then lastly we should be able to get our projection matrix. And this is because our shader will need to get this to multiply each vertex by the projection matrix. Okay, let's switch over, include. And now we can have Visual Assist create the rest for us. Perfect. To start, let's create some defaults here. So our M projection matrix will be an identity matrix to start, which means no changes, no projection. M height, we can set to something like 1080. M near, we'll set default to 0. M far to 100, and that's it. So now when we're in here, the first thing we need to do is actually calculate a projection matrix, just given our default values here. Now GLM does this for us. It has a method called glm::ortho. So glm ortho will actually create a projection matrix for us, specifically an orthographic projection matrix. And what we have to give it is the coordinate system that we want to project onto. So the left, the right, the bottom, the top, the near, and the far for the current screen. So notice we're only tracking the height, and we need to know the left and the right. What we can do here is actually have the camera have an internal aspect ratio that it wants to adhere to. That way, just given the height and an aspect ratio, we can calculate what our left and right should be. So maybe we'll do that now. Let's add a float M aspect ratio, and let's do a getter and setter as well. Great, and now we can default our aspect ratio to, let's do 16 by 9. So that's literally 16.f divided by 9.f. So with that, if we look at ortho again, it wants a left, a right, a bottom, and a top. Now it's up to us to decide where 0, 0 lies, right? 0, 0 could be right in the middle, it could be bottom left, it could be up left. That's up to us. The way I usually like to do it is to have 0, 0 right in the middle, just like we currently have with -1 to 1. So what we're going to do is first we'll calculate the half width, and we can start at negative half width for the left and positive half width for the right. And then we can do the same for the height as well. So float half width will be M height times the aspect ratio, and then times 0.5f, which gives us half. And then float half height will be M height times 0.5f. That's pretty straightforward. So now we can say projection matrix equals GLM ortho, and we'll pass in these values. So left will be negative half width, the right will be half width, and then negative half height for the bottom, half height for the top, and then we have our M near and our M far. And that's all there is to it. GLM does all the internal calculations for us to calculate this matrix. Now we do need a special include for GLM to be able to call this. It's external /GLM /GTC /matrix _ transform.hpp. And you can see GLM ortho now resolves properly. And now we have a projection matrix. So this is great. But as soon as we change our height or our aspect ratio or near or far, we're going to have to call this again. And so in these setters, we're going to want to actually set our internal value and then recalculate the projection matrix. So what we should do is just have this be its own private function. Maybe void recalculate projection matrix. That can just do this work for us. We'll call it from here. And then down here, we'll just run this code to set our projection matrix. And now it's much easier to update the projection matrix as we change these values. But before we get there, let's just quickly do the copy constructor here. So projection matrix will be other.projection matrix. Oops. There we are. And then we'll recalculate the projection matrix. Now, I know we just took their projection matrix. I feel like to be safe, we should just recalculate this because I don't know if this has been recalculated. Technically, it should be just the way I'm writing this class, but I think I'll just do that for safety. So actually, we don't even need to copy their projection matrix if we're going to recalculate it here. Okay, so set aspect ratio. Similarly, we just say M aspect ratio equals aspect ratio, and then recalculate projection matrix. For height, we'll do the same. So M height equals height, and then recalculate projection matrix. And then for ortho, okay, and that's pretty much our camera class. Now we can make some calls on this camera, have an updated projection matrix that we can then get on the other end. So back in main.cpp, let's include our camera now and actually use it. When we initialize it, we can initialize our camera here. So I'm camera. Now because our camera has a projection matrix, we're going to need to update our shaders to take in a projection matrix as well. Now we'll do a projection times the model times the position. Perfect. Now, in order to actually get our projection matrix into the shader, one thing we could do is just upload this to the shader immediately. So mshader set uniform mat4 proj mCamera get projection matrix, right? This actually should be enough to get us going. So let's go ahead and run it. And it might look like it's currently broken. I don't really see anything. But remember, our rect, it's only 1 pixel tall, and we're saying that our camera's height is 1080, so it's probably too small. Let's set the height to 1, and then set the projection matrix, and see what that looks like. And there you go. There's our rect. So our projection matrix looks like it's working. If I set it to 2, it should look just a little more zoomed out. And it does. Perfect. Now this is enough to get it working, but I have a problem with this approach. we're currently setting the projection matrix to the shader directly here. What this doesn't allow us to do is have the same shader used to render things from multiple cameras. Let's imagine a split screen game, for example. I would want to have two different cameras rendering through the same shader potentially. And what I'm saying here is that this shader at the base level will always use this camera's projection matrix. So really what we should think about is adding support for pushing and popping a camera just like we push and pop a frame buffer. This allows us to then be able to push a camera onto the render manager, and all the subsequent shaders will update projection to that currently active camera's projection matrix. And then we can start rendering things to multiple cameras without a lot of hassle. So let's do that. RenderCommands.h, scroll to the very bottom. Actually, I'll have to forward declare camera here. We'll scroll to the bottom and we'll do the same thing we did with frame buffers, but with cameras. So push camera. Perfect. Like that. And then pop camera doesn't take anything. Great. And switching to the CPP, we'll actually have to include the camera here. Push camera will just take the camera from the camera. And if cam, we'll add a push camera method to the render manager in just 1 second. And we can pop camera, and we'll call PopCamera. So render manager now needs those two additional methods here. So we have push frame buffer, pop frame buffer, and now we'll have push camera, pop camera. And then we'll need a stack of cameras, just like we have a stack of frame buffers. Perfect. We'll have to make the friend class here for push camera, pop camera, so it can access the private methods. And we'll go ahead and actually create these. I think I'll just copy up till this. So push camera takes a camera. We'll just say mcameras.push camera, and actually we don't need any of this stuff. We just want to push it back. And then for pop, same thing. So let's just make sure mcameras.size is greater than 0. Otherwise we can't pop an empty stack. And we pop it, and then that's it. I don't need to do anything else, because the only reason we need to keep these internally here is so that our render command executes can actually reference them. So the one thing we need is the ability to get the currently active camera, right? So maybe up here we'll just have an inline const graphics camera star. So we'll get the top camera on the stack, and we'll call .get on that. Actually, we might not want to just get the top in case there's no camera pushed back, so maybe we'll just do cameras.size is greater than 0. Then return that, remove this. Else, or not even an else, just return null pointer. Ugh, I don't like this. Let's not make it inline. It's too much code to make it inline. Besides, the compiler will probably make this inline for us anyways. Okay, so now we have the ability to push and pop a camera. We have a stack of cameras, and we can ask for the active camera. One thing we might want to do actually back here is assert that the camera we got is not null pointer. We'll just say camera is null. Did we do that for frame buffers? I don't think we do. Yeah. So now that we have the ability to store a camera and we can get the active camera, our render commands should actually leverage that and set them here, right? The camera will have the projection matrix internally, so we're already including camera. Maybe here after we bind everything, we can just, first we'll need the render manager, so and then auto reference cam is rm.getActiveCamera. And then if we have an active camera, we can say shader-set uniform mat4 proj, and then cam-get projection matrix. Nice. And now this will actually allow us to push and pop cameras, and this line doesn't happen in the calling code anymore. It's deferred, happens when we actually end up rendering it. The one thing that I'll just add a to-do here is we could actually make this even easier for ourselves by using something called a uniform buffer object, which we haven't gotten to yet. So I'll just say convert camera matrices to leverage UBOs. This would allow us to just set it once, and all of the shaders can look up the camera projection, for example, which might be interesting. Okay, I'm going to do that for all of these render commands here. Actually, it's just those two. Yep. And now that that's getting set properly, back in main, I shouldn't need to call this anymore. And it should instead push and pop my camera. So here I'll say push camera, camera, and we'll have a pop camera. Just like that. So if I try to run this now, we shouldn't see any difference. It should still be a height of 2 in my camera, so the image direct itself shouldn't take up my entire screen anymore. Okay, and we get an assert. What's going on here? Render manager.cpp line 103. Yeah, so it's right here. Did I get any error message before? Nope. It's just saying that mFrameBuffers.size needs to be greater than 0. So I'm trying to pop a frame buffer when I never pushed one. Interesting. Okay, let me just put a breakpoint here and run that again so we can see what the render commands queue looks like. I've got 5 things in there. The first one is, this looks like a push frame buffer. Yep, push frame buffer, and then that's a push camera. This must be the render. Yep, render array textured. So that means this is the pop camera. Yep, and this is the pop frame buffer. So I'm wondering if my copy paste was bad. It probably was. Yeah, it is. mcameras.pop. Yeah, silly. Okay, let's try that now. This is why we have a search, right, to catch these sorts of errors. Okay, now we can see that I do have my height of 2 camera being active here in the scene. What this allows me to do now is that here on the main.cpp side, I am not responsible for calling shader set uniform mat4. This push camera will ensure that it's there at the time that this is rendered, and this will internally set the shader to this camera's projection matrix. So now I should be able to just expose some controls for the camera. So maybe here, where we have these options, or maybe even just up here, instead of rect controls, we'll just call this controls. We'll have 2 float 2s for the size, and maybe just a single float for the camera height. And maybe I'll have an ImGui separator just to separate it a little bit. And the camera height will be a single float with a height. So what I'll do is I'll say float height, or cam height, equals some camera-get-height. And then here we'll potentially modify this cam height value. We're doing by 0.01 pixels. Maybe we'll do let's do half a pixel increments. Yep, this takes a reference. And now what I'll do is, instead of just setting the height every time, because that will recalculate a projection matrix, I'll instead just check if cam height's changed. So actually, I guess I'll need 2 values. Float cur cam height equals this, and then cam height equals cur cam height. And then I can just check if cam height because drag float will change its value directly, I can just check if it's not equal to cur cam height. And because we set them the same, I don't have a rounding error potential here. I can actually do it does not equal. And if so, then I'll say mCamera set height, cam height. And actually, this check could totally happen internally, and maybe I want that instead. Here, if mHeight does not equal height, then we can do all the work. Yeah, this totally makes sense. Let's do the same for everything. From near. Next one we'll need to do, it'll be a little trickier. So we'll just have a bool should recalculate. It's false. Only recalculate if we should. And then we can just say if mHeight does not equal height, we'll set it. And then should recalculate equals true. We'll do the same for all three. We could do else ifs to save some cycles here, but honestly it's going to be negligible. So mHeight or mNear, mFar, and then near and far. Let me just double check it because my copy paste is not to be trusted. mHeight doesn't equal mHeight, set mHeight to height, should calculate as true. mNear does not equal near, mNear equals near. mFar does not equal far, mFar equals far. And do it, and then if it's true, we'll actually recalculate. Okay, perfect. So with that, it actually gets simpler on the main.cpp side, which is nice. This is the kind of API we want. So yeah, we'll just do cam height, and then set height to cam height. Cool. And to prove whether or not this is working, I'll just do a print here. We should only see this trace as I modify the height. We'll need log here. Okay. So now we have this separator and then cam height, drag float, and will call set height. So now I should be able to zoom in and out, which is good. What am I missing here? Expected an expression. Oh, what is near defined by something? No way. I don't see that coming up in anywhere in my code, but it's... Oh, that's weird. Height doesn't do that. Far has this too. Far has the same problem. Weird. Okay. Let me just rename these. I mean, I don't have to rename them in the header, but that's fine. We'll just say underscore near underscore far underscore wherever you are. Yeah, that went away. Wow. Something maybe Windows specific is defining what near and far are. Oh, geez, here too. Okay. Okay. So now these controls, let's put them down here. I should now be able to modify the camera height, and maybe first we'll go to rect textured. And there it is, and you can see recalculate projection matrix only prints as I modify the height. Perfect, this lets me go into the negatives. But there we go. Now we have a legit camera that we can modify things on, and it will recalculate its projection matrix and will render according to that projection matrix, which is really cool. The next step is to give the camera a view matrix, right? Because that's the missing piece here. The camera now currently can't move. So let's go ahead and add that. Switch over to main.cpp and let's track position and rotation for our camera. So I'll do it here. So our position can be a vec3, and we'll use a float for the rotation, since we'll, for 2D, we'll only allow a rotation on the z-axis, which is the axis that comes into the screen. Okay, and then we have to be able to convert these two things into an actual matrix that we can use within the camera. And as we just did with our render commands, we'll need to be able to pull that matrix out. So just like we currently pull out the projection matrix, we'll need to pull out the view matrix. So let's add a view matrix to the camera. And what I want to do is just have it take in the position and rotation, and we'll build the matrix internally. Then we'll need another getter. And maybe we can also have a setter that takes in, I'll put it up here with the inlines, that takes in the matrix directly, if in case that's what you want to provide the API. And here we can just say view matrix equals matrix. Okay, let's get this created. And then maybe up top, first thing we'll do is set the view matrix to, again, an identity matrix, so there's no change. And then down here, it's pretty straightforward, so we can build it up with the glm mat4 view. First we translate, and we're going to translate view matrix by position. Then we can glm rotate the view matrix by the rotation, and the rotation will deal with degrees in the engine, and then we'll just convert everything to radians as needed. So glm radians rot. And because we're giving it a float, we're saying you're rotating this amount, and then we have to tell it which axes it's going to rotate on. In our particular case, we just want the z-axis, so only rotate on the z. And then as we spoke about at the beginning of the video, we have to invert the matrix. And now we can just call our set view matrix that takes in the matrix itself, and that will just set it internally. Perfect. And now here, back in main.cpp, we can just start modifying the camera position and rotation, and then just have the camera update its own view matrix. So first let's set it. Now let's add some controls to modify it. Maybe what I'll do is actually have a temporary value here. Then we'll do the same with the float camera rot. This will be in degrees, so we'll say we rotate 1.f. This takes a reference. And then we can just do that similar check we had before. So if camera pause does not equal mCamera pause, or camera rot does not equal mCamera rot, then we know we have changed the position or rotation, and we should recalculate the view matrix. And we should also update our local values. And now you might be wondering why we're doing this external to the camera, like why doesn't the camera track its own position and rotation? And this is because when we get into the entity component system, I want a transform component to be able to define the camera's position and rotation. So that's why we're putting it outside for now. So two more things. Let's update the shaders to actually take in a view matrix now. So just like projection, take in a view matrix, which we'll multiply here, projection times view times model. And we'll do the same thing up here. Projection times view times model. And then in the render commands, we just have to set it. So just like we do here with the projection, we'll set the view to get view matrix. Okay, that should be all we need. So let's run this, and we should now be able to move our camera around. And again, if I move the camera to the left, the rect should look like it's moving to the right. So here are my controls with my camera position, and I'll move my camera to the right. There it is. Move camera to the left, up and down, and then Z. Obviously, you'll just see it go out of that near and far clipping range there. But there you go, and then our rotation. So you can see our rotation here is working as expected. Let's switch to this. There we go. So we're always rotating about the point at which we're in, which makes sense. And there is our view matrix. Now, there's one thing I noticed. I tried to double click on these. You should be able to set the text. Like this should convert into a text box. If you double click this, you can type the number in. So let's figure out why that's not working. This usually happens when ImGui isn't getting the STL events properly. So let's just go over to window.cpp because I have an ImGui window.cpp and it should, it has this handle STL event and it processes the events. So we have to make sure this is getting called, which should be happening in window.cpp. When we pump the events, it's not getting called. So that's what I missed there. So imGui window.handle STL event, and you pass in the current event. So within our poll event loop, whatever the current event was, we can handle it on our side, and then we'll let the ImGui window handle it itself as well, so that ImGui can handle the event properly. So let's run this now, and this actually should be fully functional. So now I can move the position, but I can also double click, and yeah, there we go. Now I can type in like 1. So I can have the camera at position 1, the rect at position -1. You can see it moves further to the left, or the rect at position 1, and now it's back to center. So the rect is both in world space in position 1, and the camera is in position 1, which means we see it right in the middle of our camera, and it's not, that's the middle there. There we go. Maybe I'll move this to the bottom here so we can see it better. But now we have a camera that we can change the projection matrix on. We have a camera that we can move around our scene. So that's it for today. Thanks so much for watching, and I'll see you next time. Cheers.